Hello, we are seeing that special theory of relativity is about what is absolute and what is relative. The laws of physics are absolute, that's the principle of relativity. Speed of light is absolute, that's the principle of constancy of the speed of light. This second could also be thought as a consequence of the first one, as Maxwell's equations lead to a very specific value for the speed of light. And all laws of physics are the same independent of the inertial reference frame. This constant speed of light is a cornerstone in special relativity, and it is something we can hang on to, something that does not depend on who is observing. We saw that the order of a sequence of events depends on the observer. The time elapsed between two events depends on the observer. The length of an object depends on the observer. But the speed of light is our base, is something that will remain the same. Are there other parameters that are absolute, that are invariant? Just for fun, let's calculate the following relationship.
So I'm going to change this delta t prime and delta tx, which is just the time between two events, from this reference frame S prime to a reference frame X. So I'm just going to make a transformation of coordinates for a transformation of reference frame. But here I have the Lorentz transformations that when I know X, that is X as a function of X prime and T as a function of T prime X prime. First I'm going to do is write the inverse of that. So if one reference frame has a velocity plus v, then with respect to the other one, then the other one is going to have a velocity of negative v with respect to the first one. So these two equations will be rewritten as x prime is equals to gamma x minus vt and t prime is equals to gamma t minus vx over c squared. So these are Lorentz transformation equation from the prime to the unprime reference frame and from the unprime to the prime reference frame. So just for fun, I'm going to transform these primes into non-prime. So I will substitute this delta t prime by this thing here. So this is going to be parentheses t c delta t. So c gamma delta t minus v delta x over c square minus this delta x prime square, which is going to be this gamma delta x minus v delta t squared. Okay, now let's solve these squares here. I will take out this c square gamma square that for the first term. For the second one, I have this negative gamma squared multiplied by the square of the first one. So that I have just calculated both the squares, and I'm gonna have a look at all this mess I have here. For example, I can cancel this c squared with that c squared, and then I will have negative 2 c squared gamma squared delta t v delta x, sorry, not with the c squared, which is 2, I have a positive 2 gamma delta x delta t v. So this term will be cancelled with the other one. So this term here cancels this other term here, and this gets a little bit simplified. This is equal to the first one. Okay, c squared. That's c squared for everybody, right? No, sorry, it's gamma squared for everybody. And then it's going to be this c squared delta t squared. That's this first term. This other term, I will simplify this c. So I will take the gamma squared out of there. So this is going to be plus v squared delta x squared over c squared. Now this term, remember that one was cancelled with this one. Next one is this. Gamma squared is out of there, so this is going to be negative delta x squared. Here, this is negative v squared delta t squared. Okay, fine. Let's continue. I have this gamma squared out of here, and I can do the following. I will group delta t and then delta x, so I have delta t square parenthesis c square minus this v square here, so minus v squared. Whoop. And now for the delta x plus delta x, let me write negative delta x. Yep, I will first put this negative term here, which is 1 minus this beta square, because the delta x square is out here, and then b square over c square is beta square. Okay, now here I'm gonna take out a c square out of there, so I'm gonna write the following. This gamma square is out of everything. Now I have this c square delta t square parentheses. This is going to be 1 minus beta square minus delta x square parentheses 1 minus beta square, and it's closed. Now that I have that, what I'm going to do is, oh, look at this, 1 minus beta square, 1 minus beta square. I can take it out of this mess, and happens that gamma square is 1 over 1 minus beta square. So I will rewrite it here, equals 2. So this gamma square is 1 over 1 minus beta squared. Then I take out of the parentheses 1 minus beta square, and I have in here that this is c square delta t square minus delta x square. So this cancels that, and I get c square delta t square minus delta x square. But let's look at the beginning. Let's go back at the beginning and have this. So this is exactly the same as that, but this has primes, this has no primes. So I can say right here delta t prime square minus delta x prime square, and this happens to be an invariant magnitude. I have that this c square delta t square minus delta x square is the same for both reference frames. So it's the same for all reference frames. So this magnitude is another invariant, something that doesn't change. The numerical value is the same for all observers in all reference frames. Now, let me erase a little bit this. And let me define delta s square as c square delta t square minus delta x square minus delta y square minus delta z square. That's just a generalization to all 4 coordinates, 4 dimensions. This we call the space-time invariant or interval. And this magnitude is invariant, so that's the distance between any 2 events. If one of the events is right at the origin of coordinates, just to simplify stuff, then we can just remove the deltas, and you can also find in the literature that s square is equals to ct square minus r square. This is the space-time interval, yes, and that's an invariant.
Well, this is another invariant, another absolute magnitude, something that all observers will agree upon. Something that has the same numerical value for everyone. This space-time interval, if you look at it closely, you can see that this term here resembles Pythagoras' theorem. Well, it is the distance between 2 points. But we have it in negative, and we add here the time distance. So this is how we measure the whole space-time distance between 2 events in special relativity. Yes, you can always measure physical spatial distance between 2 events, but the space-time distance is given by s squared, by the space-time interval, and this distance is an invariant magnitude.